Yeah, so I think we can start. Let me share the screen. One second, guys. Yeah, so good evening, all. Welcome to this NPTEL PMRF teaching assistantship session. So, yeah, so myself, Ritu Sawat. I'm currently working as a Prime Minister Research Fellow in Department of Earthquake Engineering from IIT Roorkee. Those who are joining this session for the first time, let me tell you, these are the sessions which are particularly meant to interact with our learners along with your ongoing NPTEL courses. Along with that, we'll be discussing some of the important concepts which will be required to solve your assignment problems. We'll be solving some of the sample questions. Along with that, we'll be solving some of the doubts. Apart from that, if you are having any other non-technical query which you want to discuss, please feel free to discuss. So let's start with our session today. So anybody join? Not yet. So let's start. So you are given with a spring and a dashboard which are attached to a body weighing 150 Newton. The spring constant is 3 kN per meter and the dashboard has a resistance of 0.65 Newton at a velocity of 0.05 meter per second. If the system is set to a motion, the system is whether it is over damped, under damped, critically damped or none of the above. So let's check the answer for this. So in this, you have been given the spring constant, which is given to you as 3 kilonewton per meters. The dashboard. So the dashboard force, which is given to you as 0.65 Newton. Dashboard force is also given as CV dot, which is your 0.65 Newton. And with the help of this, basically we can calculate, since the velocity has been given to you. So 0.65 by 0.05. 0.65 into 100 by 5, 20, and then 6.5 into 2. So C is basically your 30 Newton per meter, Newton second per meter. So now if I want to calculate if the system is set to whether the system is over damped, under damped, or critically damped. So first let's calculate the C by 2m. So C is your 30, 2, and then mass is basically your 150 into 9.8. So this is your C by 2m. So let's first calculate this. So this is the value which we are getting as a 0.245, and let's calculate the root over k by m. K is your 3 kilometer per meter, and mass is basically 150 into 9.8. So so we are getting it as 0.443. So since your C by 2m is basically root over k by m, so it's your none other than under damped system. So correct answer is option B, which is your under damped system. Moving to question number 2. So you have been given with uh, okay, this also need to be multiplied by 1000. So anyways, so this value is basically is greater than your C by 2m. So this is under damped system. So coming to question number 2, which has been given. So you have been given with the counter rotating eccentric mass exciter, which is used to produce force oscillation of a spring supported mass. By varying the speed of the rotation, a resonant amplitude of 4 mm was recorded. When the speed of the rotation was increased considerably beyond the resonant frequency, the amplitude appeared to approach the constant value of 0.5 mm. The damping factor in percentage of the system is 2.20, 5.67, 6.25, or 7.87. Yeah, so let's check the answer. So in this, it's basically given like this. So your U max is none other than your 4 mm. Your U max by M E by M is basically given like this. So this is your 1 upon 2d root over 1 minus 2d square. So visually your D values damping ratio is very small. So we consider it very less. So this entity become negligible. So this is 1 by 2d. So now calculate this. So your Umax, by varying the speed of the rotation, a resonant amplitude 4 mm is observed, and your mass at centric value is basically MEAM. The amplitude appeared to approach a constant value of 0.5 mm. So basically your ME by M value is your 0.5 mm. So power by 0.5, and this is your 1 by 2d. So D is your 8 by 0.5, which is your D is your, sorry, so D is basically your 1 by 8 upon 0.5. So this is your D is your 1 by 16. So this is your 0.62, 0.0625. And if you see in the percentage, D in percentage is your none other than your 6.25 percentage. Yeah, so correct answer is this. The damping factor in the system is basically 6.25 percentage. Moving to question number third. You have been given with a single degree freedom system which is excited by a sinusoidal force. At resonance, the amplitude of the displacement was measured to be 3 mm at an exciting frequency of 1/10 of the natural frequency of the system. The displacement amplitude was measured to be 0.2 mm and the damping factor of the system in percentage is So what is the damping factor of the system in percentage? So you have been given with a single degree of freedom system. Let's say you excited by a sinusoidal force. At resonance, the amplitude of the displacement was measured to be 3 mm. So when the resonance occurs, the condition occurs, the displacement is measured to be 3 mm. At an exciting frequency of 1/10 of the natural frequency of the system, the displacement amplitude was measured to be 0.2 mm. The damping factor of the system in percentage is. Yeah, so let's check the answer for this. So with the same question, they are basically saying that U max is basically 3 mm, and at an exciting frequency of 1/10 of the natural frequency of the system. So your U max upon F naught by K, which is your U max by U naught, we know is given by 1 by 2D. So when the exciting frequency is 1/10 of the natural frequency of the system, means it's very low. So your U max is basically 3 and your U naught is basically 0.2. So this is your 1 by 2D. So if we evaluate this, so D is your 0.2 by 2 into 1 by 3. So which is 1 by 30. So damping is basically 3.33. So if we 3.3 percentage. So correct answer is your option A. Means when it is saying a 1/10 of the natural frequency of the system, so we can almost consider it as the static position. So you note you can count it as 0.2, and with the help of this you can calculate what is the damping factor, which is your 3.33%. Moving to question number 4. So you are having a body which is weighing 500 Newton and it is suspended from a spring which deflects 10 mm under the load. It is subjected to damping effect adjusted to a value 0.3 times that required for critical damping. The undamped natural frequency of the vibration in radian per second is. So let's solve this. So sorry. So you have been given that weight of a body is 500 Newton, and then the mass is basically 500 by 9.81. It deflects, so the deflection which is observed is 10 mm. And your damping is none other than your C by Cc. So D is your 0.3. So similarly C is your 0.3 Cc. So let's check this. So omega n is your root over k by n. So k you can basically get it from this. Five hundred by 10 mm into 1000. So which is your 5 into 10 to the power 5 Newton per meter. But you can also write 5 into Newton per mm. So if I calculate this, so yeah, here you need to put in the amperes. So 5 into 10 is over 5. And your mass, which you will be having, will be 500 into 9.81. So omega n, which you will get here, is So I'm getting as omega 99, but they are getting is this. I'm not sure why. I'm not sure. The answer which I am getting. So the undamped natural frequency, I'm getting it as 99 radian per second. I'm not sure how they are getting this. Okay, it's not 5 into 10 to the power 5. Rather, it should be 5 into 1. Okay, it's 5 raised to the power 10 4 Newton per meter. Yeah, now it makes sense. Sorry. So we'll be having 31.62 radian per second. Now let's calculate the damped natural frequency. So we know the damped natural frequency is given by omega d is equals to omega n root over 1 minus xi square. So omega n, which is given to you, is 31.62 root over 1 minus xi square. Xi is your xi is 0.3. So let's calculate this. So which is your 29.96, which is your closer to, I guess, option B, which is your 30.16. So correct answer is, yeah, option B, 30.16. Let's move to question number 6. So you have been given with the ratio of the successive peak amplitude. Okay, so now basically they are asking what is the ratio of the successive peak amplitude of the vibration for the system, which we have question number 4. So in this particular damped system, what is the ratio of the peak first to peak amplitude? Like if we'll see. Yeah, so let's check the answer. So there's another way to calculate the damping ratio, which is given by delta is equals to 2 pi d. So which is your ln z1 by z2. So your z1 by z2 is your e to the power 2 pi d. So your z1 by z2 which is your 6.58. So the ratio between two successive peak amplitudes is basically e to the power 2 pi d, which is your none other than 6.58. Moving to question number 7. So in a cyclic plate load test on a plate which is 0.6 meter by 0.6 meter side, it settles 0.6 mm under pressure of 18 kPa. On basically unloading, you observed a plate settlement which was 0.5 mm. The value of the coefficient of the elastic uniform compression of the soil is. So it settles basically 0.6 mm under a pressure of 18 kPa. On unloading, you observe the plate settlement was 0.5 mm. The value of the coefficient of elastic uniform compression of the soil is. So the pressure which is given to you is 18 kPa and the plate size plate is your zero point 0.6 by zero point 0.6 and your delta means the place which it settled is 0.60 mm, and when unloaded, so delta unloading, you see this as 0.50 mm. Now you need to calculate what is the value of the coefficient of the elastic uniform compression of the soil. So which is given by Cu upon P upon delta C. So P is your 18 kPa, delta C is your 0.60 mm. Okay, delta C is basically the difference between the loading and the unloading condition. So on loading, the settlement was observed at 0.60, and the unloading it was observed as a 0.50. So delta C you will basically observe is your 0.10 mm. So P is your 18 kilonewton per meter square, converting into the newton per meter square. This is your 0.1 mm. So keeping it on the P as a kilometer per meter square only, but converting this into the meter, you will get something like this. So 1818. So 1.8 into 10 to the power 5 kilonewton per meter square, which is the kilometer per meter cube. Yeah, kilometer per meter cube. So correct answer is option E, which is your 1.8 into 10 to the power 5 kilonewton per meter cube. Moving to question number 8, you are having a mass of attached to a spring of 7 Newton per meter annum. It is having a viscous damping, has a viscous damping device. When the mass was displaced and released, ratio of the consecutive amplitudes was 12/5. The damping factor of the system in percentages. So what is the damping factor of the system? So let's calculate this. So for answer, Z1 by Z2, ln Z1 by Z2 is basically your 2 pi t, we know, and where your Z1 by Z2 is the ratio of the peak amplitude. So now D is your 1 upon 2 pi ln Z1 by Z2, 1 upon 2 pi into ln 12 by 5. So let's calculate this. So your damping ratio is basically a 0.138. And if you see in the percentage, it somewhere comes around 13.8, which is nearly equals to 13.93 percentage, which is option C. So correct answer is yes, it's option C. 13.93 percentage. Yeah, this is another question. So now let's move it to the brace excavation work. So you are having a trench of 5 meter wide, 10 meter long, and it's excavated in a medium dense sand. The side of the trench are supported with the sheet pile walls fixed in a place by a strut and a well, which is that is a brace excavation. Assuming gamma is 18 kN per meter cube and phi is 30 degree, what is the maximum pressure which is against the uh, sheet pile wall?
So let's calculate this. So answer, so your pressure is 0.65 H gamma Ka 0.65, and is your 10-meter long. Gamma is basically 18. Ka is your 1 minus sine phi upon 1 plus sine phi. 1 sine 31 by 2 upon 1 plus 1 by 2, which is your 1 by 3. So K is your 1 by 3. If we calculate 3, so 0.65 into 60. 0.65 into 60, it basically turn out as a 39. Correct answer is option B, which is your 39 kilo. Let's move to question number 11. So in this, basically the proposed brace excavation at a site with the apparent pressure diagram is shown in the figure. The studs are spaced longitudinally at 4.4 center to center, and the sheet piles are pinned or hinged at stud level B and C. What is the load on the stud A in kilonewton is? So everything is
So let's check the answer. Answer is option D. Let's see how we have come to this. So let's say if you are having a wall, so that's how the tributary diagram basically looks like. So here it's basically your 0.25 H. Here will be your 0.5 H, and here again your will be 0.25 H. So strut, so 0.25 H is basically, so your whole H is 12 meter. So 0.25, so this is your 3 meter. This is your 6 meter, and this is again your 3 meter, right? Yeah. And now your strut is basically located at the position of 1.5 meter, somewhere in the middle. Your strut is located, which is your 1.5. And somewhere at the 3 meter, this is your P1, and somewhere at the 4.5 meter, so this is 3 meter. So this is your 4.5 meter. And the width of this tributary diagram is 0.25 gamma h. So now they are basically talking about how much is the load on the strut A. So basically this is basically pin connection, so we can take moment about this. So this is your A strut, this is your B strut. So your 0.25 gamma h,
gamma is your 18.5 and height is your 12. So this will come out as a 55.5 kilonewton per meter square. So now let's see this. So if I'll take the sigma mb is equals to 0, so this is basically 3 times your RA, and then this will be your solid stress diagram. Yeah, so this is basically your 1.5 into, so the total width is your 55.5. If I'll just take the rectangle first, so this is your, the triangle is basically a 3 meter and this is your 4.5 meter. So 4.5 minus 3, so this is your 1.5 into 55.5 into 1.5 by 2 plus half into 55.5 into 3 into 1.5 plus 1. So is this the case? Let's calculate this. So R is your 1 by 3. So I'm getting RAS 90.1875. So which is kilonewton per meter. And since it has been given, the spacing between the studs is 4.4 meter. So the correct answer for this, so load in strut A totally, which it is need to bear, is 90.1875 into 4.4, which is your 90.1875 into 4.4, which is your none other than 396.825 kilonewton 1010. Yes. So the correct answer is option D. Okay, let's move to question number 12. So in question number 12, basically it's asking, as we have calculated for the A, how much the load will be there on strut B in kilonewton. So let's see this also. Answer is 702.2 kilonewton. Let's see how it is. So again, so this was your pressure diagram. So this is your 0.25 gamma h. Yes. And this is your 0.25 h. This is your 0.5 h. And this is your 0.25 h. Okay, so here is your one strut, which is your 12.253 meter. This is your 6 meter. So here is your first strut, which is your A. So this is your RE. This is your RB. This is your RC. Okay. Now, basically, your RB and RC. So it will get split into two because first half of the part of the strut of at C will bear the load above the C and half will bear below it. Similarly, B half of the load, half of the capacity of the strut B will be utilized in resisting the pressure which is coming from the soil above, and the half of the capacity will be utilized well below. So let us split into this. So this is your RB2 and RB1. This is your RC2 and this is your RC1. So we know uh, basically whole RA plus RB1 is resisting this stress diagram if we see. Okay, so we need to utilize the uh, force which is coming from this pressure from the soil behind. So this is basically your how much its strut is at the 3 meter. Yeah, so this whole that the whole thing is your 4.5. So half into 4.5 minus 3. So half into 4.5 4.5 minus 3, your 1.5, and this is your 0.25 gamma h, which is your 55.5. Half 4.5, 1.5 into 55.5. So if we calculate the RB1 from this, so this is somewhere your value. Okay, so this will not resist this whole force. This will resist your this force. Which is your first your this diagram will come into picture, and then this diagram will come into picture. No, it will resist the whole force here. I'm getting confused. So this is your half into 4.5 plus 1.5 into 55.5. So RB, so it's basically 166.5 minus RA, and your RA was 90.1875, which is your RB1 value. If I'll see, is your 76.24 kilonewton per meter, and 76.24 into 4.4, which is your 335.456 kilonewton. Similarly, your RB2 plus RC1 will resist this. So this will be your 0.25 gamma H into 3. So RB2 and RC1 will be equal because they are resisting the equal load. So RB2 will be your E by 2, which is your 166.5 by 2, which is your 83.25. So your whole, so total reaction in B will be equals to RB1 plus RB2, which is your 333.5.456 plus 83.25, which is your 335.456 plus 83.25, which will give the answer as 418.706. Okay, this also need to be multiplied with 4.4. I forgot. So this is your 4.4. So 335.456 plus 83.25 into 4.4, which will give you answer something like this, 701.756 kilonewton. So yeah, we are closer to our answer, 702.2 kilonewton. So correct answer is 702.2 kilonewton. So I think that's it for today. If you guys are going to watch this video at the latest stage, you can post your query in the comment section of the YouTube video. I'll definitely address your queries over there. Thank you so much. Please try to be available in the last class. The on next Tuesday we'll be having the last session. Thank you so much for joining.